Goodness, I'm running 15 seconds late already. Good morning, everybody. Good news, we got the overhead projector working. Actually, when you left, they fixed it. All right. Yesterday, I guess I'm saying that, but anyways, on Monday, I was talking about the atom, and we're getting into some chemistry stuff now. And on Monday, I talked about the subatomic particles. Those are the particles that make up every atom of every element. And they are the electron, proton, neutron. The electron has a negative charge, and you should know this, again. And the proton has a positive charge, and the neutron has no charge. And, I'm feeling a group participation coming on. Everybody together, the subatomic particles. First one. All right, everybody get in phase. Together, first one. Electrons. Next one. Protons. Last one. Neutrons. I think I pressed my luck pushing enough today. All right, and you should know these because every element, gold, is plastic, which is not elements, but anything you see here except the light itself is made up of those three subatomic particles that make up the atoms that make up everything you see in this room. And those are the subatomic particles. And I talked on Monday about Rutherford's gold foil experiment. And the important thing to remember is, one, Rutherford was able to deduce, that's a fancy word I'm using today, to figure out, that's what deduce means, that the atom has a nucleus, and the nucleus is very dense, and the nucleus only contains protons and neutrons. You should know that. The nucleus, which is the center of every atom, contains only protons and neutrons. So if I ask on a test, what's in the nucleus, everybody should know protons and neutrons. Now, an important aspect of every element's atom, or every element, is called the atomic number. And the atomic number, by definition, is the number of protons an atom has. So atomic number equals the number of protons equals the number of protons. Now, I don't have a slide for this. I'll write it the old-fashioned way on the board. And I have a slide later on when we talk about this. All atoms of the elements have a net zero charge. There's no charge on it. Now, if a proton is a +1 and every atom has a net zero charge, see, it even says it on the board, must be true, it is, then the atomic number also equals the number of electrons. once again, I'm going to be subtle this morning. Again, important thing, atomic number of an element. That tells you how many protons are in that element. It tells you how many electrons are in that element. So once you know the atomic number, you know how many protons are in that element, you know how many electrons. It turns out that's an important thing to know. Let's check. I missed something. Thought I had it in here. Let's do a little practice. Here's the periodic table you'll be using. I thought I had it in the lecture folder, but I'll scan it sometime today and put a copy in. Let's take a look at it. Now, on every test in the final, at the back of your packet or the paid test I give out, you'll get a copy of this. And notice, there are no names on there. You have to know the name and the symbol. So if I ask you, for example, what is the chemical symbol of sodium? Well, you have to know it's Na, which is over here. And don't forget the first column, alkaline metal. This is the alkaline earth metal, quick review from chapter 2. Over here I have the halogens. Finally here I have the noble gases. And those are key columns or families or groups you should know. So anyways, you notice it's the periodic table. It's got numbers on there too. Let's look at an important number. The number on the top in this periodic table is on the right. Sometimes you'll see it here, but it's always on the top. That's the atomic number of an element. So if I ask, what's the atomic number of carbon? Ooh, you gotta know carbon is C, and notice it has an atomic number of 6. Now I could next ask is, how many electrons and protons does carbon have? Ooh, how do you know? Because you know the atomic number equals the number of protons equals the number of electrons. If the atomic number of carbon equals 6, how many electrons and protons does carbon have? 6 protons. And 6 electrons. Let's do some more practice, because practice is good for your brain, helps you learn it. And if I ask, how many protons and electrons does lithium have? Well, first of all, what's the chemical symbol for lithium? Li. You'll see it right up there. And what's its atomic number? It's the number on top, which is 3. Therefore, lithium has 3 protons and 3 electrons. You know I'm going to share the fun, so why don't you figure out how many electrons and protons oxygen has? All right, why don't you try the first one? And sometime in the future, on a piece of paper I might hand out in this class, we'll say, how many electrons and protons does the following elements have? And it might be 1 to 2 points each, depending on my mood. Coming up soon, because I got to write test number 1 soon. It's coming up in a couple weeks. And how do you do that? I'll let you try oxygen first. Big hand, big hand. And if we look over at the periodic table, first of all, you have to find oxygen. Oxygen's right there, O. What's its atomic number? The number up here, 8. Therefore, you know oxygen has 8 protons and 8 electrons. I'm going to abbreviate because I feel lazy this morning. All right, next one. Why don't you try how many electrons and protons does bromine have? Everybody see the table okay? First of all, you got to find out what's the chemical symbol for bromine. In case you haven't learned it, and I hope you have, work on it this weekend because there's no football on, it's gone. Well, it might be an all-star game, but anyways. And Sunday there's a good soccer game going, but other than that, study hard. All right, question is, what's the chemical symbol of bromine? It's Br. Where is it located in the halogens? What's its atomic number? 35. The atomic number tells you the number of protons, number of electrons. Therefore, bromine has 35 protons and 35 electrons. Next one. Ooh, one of my favorites, because I worked with it a lot in grad school, argon. How many electrons and protons does argon have? Well, first of all, you got to know the chemical symbol of argon. I'll help you out. Ar. By the way, I don't do that during the test. All right, let's find it. Argon. It's a noble gas. What's its atomic number? 18. Therefore, how many protons, how many electrons does argon have? 18 protons, 18 electrons. Again, you should know the atomic number, which is a very important number, gives you the number of protons and the number of electrons. Oh, let's do one more. Let me think of a good one. Ah, here's a good one. I don't know my alphabet. Oh, I do. Na, if you don't know the chemical symbol of sodium, if you're having trouble with the chemical symbol, you should look at it. I'm only going to ask 37 from this table. All right, sodium, Na. It's an alkali metal. It's over here. What's its atomic number? On top, you'll see 11. If you look in the box. And therefore, how many electrons does sodium have? How many protons? That's because the atomic number equals number of protons and number of electrons. All right, next couple of slides. I think I've used this analogy. It's been a while. Click. I'm turning the switch. Will this be on the test to the off position? And there's some background information to when I do turn it back on. All right, there's an important number on the periodic table called the atomic mass number. And I'll usually say atomic weight. Wait, I think I asked this once before, but I'll ask again. In the next, let's say 3 or 4 months, anybody planning on leaving the planet? You gonna stay on Earth? Everybody? Yep, so I can use mass and weight interchangeably. Other chemists would argue with me, but I know I'm right. Anyways, by definition, the atomic mass number is the sum of the number of protons and neutrons in the nucleus, because the nucleus is where the protons and neutrons are. Well, it turns out that they're different, and here's a word that I won't ask you, called isotopes of the elements. Again, it switches off, but an isotope are atoms of the same element that have different number of neutrons. How many of you have heard of carbon-14 dating in archaeology? Some of you? Carbon normally exists as 12, and it can have also 14 for its atomic weight, or mass weight, atomic mass, and that is different isotopes. It turns out chemists have the ability to determine on our planet the abundance, how much of each isotope there is of each element. And that's been done. Now, when we talk about, I forgot to take this out. I'm skipping this. Switch is still off. Now, there's a very useful number on the periodic table called the atomic mass, which I'll also call the atomic weight. And this is a weighted average of all the natural occurring isotopes of the elements based on the abundance, which means how much, and the mass. So if you have 95% or 98% carbon that has a weight of 12 and less than 1% 14, you take 98 times 12 and 1% times 14, you add it together. I just made up those numbers in my head, but what that does is allows you to, there's the slide I was looking for, allows you to find the following. If we look at carbon, you'll see the number underneath the symbol, 12.011. And that's the weighted average of all the carbon-12. There's a little bit of 13, very little, and 14, not that much. And you add it together, and you get 12.011. And if you look under each of these chemical symbols on the periodic table, and all of them are the same, wherever you find your periodic table, you'll see the atomic mass or weight. I'll use the term weight because I like to. And sodium is 22.989. Actually, you can find tables where there are more significant figures. Now, you want to understand the significance of what I'm going to say now, but I'm going to give you a nice gift. When we have to use those numbers, it will be important. In my class, and also when I've been a chemist, I'm doing calculations with them in industry, I round off my atomic masses or weights to 3 significant figures. And that's going to make your life a lot easier later on in the semester. So you can say, thank me, Dr. White, later. But anyways, when you figure out what that does. But for now, if we look at, say, chlorine, the atomic weight, without rounding it off now, is 35.453. And if you look at oxygen, it's 15.999. How would you round that off to 3 significant figures? 16.0. And I'll show you how to do that. And that's the atomic weights. We won't use it for a while, but we will use it later in the semester, especially for test 2, 3, somewhat 4, and the final. But I'll teach you how to do that. I think you figured that. Let's look at the next slide, because we're going to come back to the periodic table. And it's practice time once again. And let's look at, do a couple more. And why don't you try this on your own? You have a periodic table. Why don't you find out how many electrons and protons are in potassium, nitrogen, and chlorine? See the sign sheet, make it around to everybody. Thank you. If you came in late, don't forget to sign in, it's up here. All right, everybody done? Let's do it. First one, potassium. First thing you have to know is what's the chemical symbol for that. Okay, interesting story. If back when, now it's on the internet, but in certain chemical catalogs, if I were looking for something in the index at the back for potassium or something with potassium, I'd always turn to K first, and oh no, it's English, I have to put the P there. But anyways, potassium, alkali metal, K. What's its atomic number? 19. The atomic number tells you how many protons and electrons. Therefore, potassium has 19 protons, 19 electrons. As you can see the number right there. Next one, nitrogen. What's the chemical symbol? By the way, this is a sneaky way of me also testing you know your names as chemical symbols. And it's N, nitrogen, located right here. And what's its atomic number? 7. Therefore, it has 7 protons and 7 electrons. And finally, one of my favorite elements, because I used it a lot in grad school, chlorine. And chlorine, Cl. And what's its atomic number? Number on top, 17. Therefore, it has 17 protons and 17 electrons. And if we looked at, and we'll go through this later on when we need it, chlorine, here's its atomic weight. Argon is over here. I'll never be a hand model on TV. And one more. Oh, I forgot to polish my nails. I don't. And if we look over here, oh, let's look at something that's important. Calcium, which is good for strong bones. And there's its atomic number, 20, meaning 20 protons, 20 electrons. And its weight is 40.078. By the way, this switches on, you know how to do the following type of skill. All right, let's move on. Next couple of slides is background information, so I'll turn the switch click off. This won't be asked on the test. But when we talk about atom, you now know in the center, the nucleus has the protons and neutrons. And the question is, where are those electrons? Well, they're all around the nucleus. And a very important study is electronic structure. Where are the electrons? And in order to talk about that, I need to digress a little and talk about something called electromagnetic radiation. That's energy that travels through waves through space. Light is one. My cell phone is getting stuff by electromagnetic radiation, the waves from the cell tower that's sending to my phone and yours, and there are others like X-ray and so on. Now, when we talk about a wave, if you've ever seen waves coming in from the Pacific or Atlantic Ocean, gone to California a lot when I was working in industry, and so I got to see that when I had some free time. Or there was this one hotel that was right on the ocean at the front. That was nice. That was in Laguna Beach. But anyways, how far apart the waves are, we call wavelengths, and how quickly they come in to the shore, or to you, the observer, is called the frequency. And electromagnetic radiation is like ocean waves. It has both wavelength and frequency. again, switches off. Now, when we talk about electromagnetic radiation, we have the electromagnetic spectrum. It's an arrangement of all various forms of electromagnetic energy in order of decreasing energy. Different types of waves, like radio, X-ray, have different energies. Don't you love Google? Now, if we look at this diagram or picture of the electromagnetic radiation, over here we have high energy, and as we move here, we get lower energy. And if you notice, right in the center, there's a spot where the visible light is located. And visible light, like the white light, is made up in sunlight of different wavelengths, which are different colors. I still remember from high school, Roy G. Biv. Did anybody learn that? Red? Never mind. Anyways, over here, these are very short frequency, or short wavelength, high frequency, high energy. Gamma radiation is very dangerous. It made the Hulk. No, it didn't. But anyways, and X-ray, and then we get the ultraviolet, visible, infrared, microwave, and radio. And why are we learning about this? Good question. Let's get back to our slides. It turns out if you take an element and heat it up in a black box, it will give off light, but not white light. It will give off what's called the atomic spectrum. The light coming off that can go through a prism and be separated into different bands or colors. How many of you have ever played with a prism? You have a glass prism? I have a nice collection at home. Yes, I'm a scientist. I liked them when I was a little boy, even I had a collection. You know, a couple of them nice big ones. But anyways, when you put light through a prism, and see it this way. If you were to take sodium metal and heat it up and put it through a prism, instead of seeing all the visible light, you only see certain bands. Same thing with neon. That's why neon light has a certain color. Neon signs have a certain color. You mix it with other gases, it becomes a different color. Same thing with hydrogen, calcium, magnesium. When you put it through a prism, it separates it into these different bands. And that's extremely important because about the turn of the 1900s, late 1800s, 1900s, chemists were able to use that knowledge to come up with different energy levels, and switch is still off, that's associated with the lines in the atomic spectra. And we call these energy levels principal quantum numbers N, and they're also called shells. And the shells are where the electrons are. And the switch is off on this slide. If you want to copy it down, I'll wait a second. Don't forget, time for commercial from Dr. White. Anything you see up here is on Blackboard, which you can download at your convenience whenever you like. So we have these shells, which are indicated by the different lines in the atomic spectrum. switches on, full blast, click. All right, where are the electrons? It turns out that's very important to know, because that's how everything around you is held together. And the electrons are first of all located in an electron shell. Electron shell is the region around the nucleus that contains electrons that have approximately the same energy and spend most of their time approximately the same distance from the nucleus. By the way, electrons don't look like the planets going around the sun, even though sometimes people like to show that. That's not how they really are. But they're in a certain distance away from the nucleus. That's the shell. Now, each shell has subshells. And those subshells are the region of space within an electron shell that contain the electrons that have the same energy, meaning they're the same distance and the same energy. So you have shells, and each shell has a subshell. Who said that 5 times quickly? We have the nucleus in the center, and around it at a certain distance you have the shells. Now if I take this shell and magnify it, each shell has subshells. Relax, it'll make sense in a little while. If not, don't forget in my class, I haven't said this in a long time, there's no such thing as a dumb question, so feel free to ask. So you have a shell, which is a certain distance from the nucleus, which contains the protons and the neutrons, and the electrons are in the shells, but their locate shell, like this one, has subshells where you can have electrons located. And it turns out which shell and subshell electrons are for the various elements has profound effect on their chemistry, how they make things and form things. Like how hydrogen and oxygen forms water, how carbon, hydrogen, and other atoms forms my skin or what's left of my hair, things like that, and you too. All right, let's look at the following slide. Now, in the past, I would say you have to memorize this. This slide, I will be putting in important information. But still, now the shells have very complex names. The first shell is 1. The second shell is 2. Hard names to remember. Third shell is 3, 4, and so on. And those are the shell names. And when we have the shells, I don't have on there, shell 1 has the lowest energy. When you go down the higher shell number, higher energy. And this will, you'll see is important where the electrons are. Now, each shell has a subshell. And if we look at this, this is real complex. Shell 1 has 1 subshell. Shell 2 has 2 2 subshells. Shell 3, say that 5 times, has 3 subshells. And finally, shell 4 has 4 subshells. So the different shells have different amount of subshells. And this chart you'll be given on test number 1 when you'll need it, and the final. So we have shells, that's where the electrons have approximately the same energy and the same distance from the nucleus where they spend their time. Now, let's look at the subshell. Everybody have this copy down? Going once, twice? Remember, I have the fastest mouse wheel finger this side or the other side of Mississippi. Now, subshells have letter names. They are S, P, D, and F. And in order of lowest to highest energy, S is the lowest, P is next lowest, D and F is the highest. Now I'll give that to you. Now this you don't have to know, but a couple of years ago a student asked me, where do those letters come from? And I'd forgotten. So I went and looked it up again. And it turns out when they're doing spectrophotometry, in other words, looking at the lines, atomic spectra of different elements, someone came up with, oh, let's call them based on how strong they are to light, different names. And someone came up with sharp, principal, diffuse, and fundamental. How they came up with that, I have no idea. But that's what S, P, D, and F. I'll never ask you this on a test. And you people in front have everybody behind you is witness I said that. But in case you were wondering where those letters come from, that's where they come from. So you have a shell that has a certain amount of subshells, and those are the names, and S is the lowest energy, F is the highest. And it turns out knowing which order of energy is important to figure out where do the electrons go. Now, not all subshells are created equal. What do I mean by that? S, you can only put 2 shell electrons in. The subshell P, you can only put 6 electrons. D, you can put up to maximum 10, and F, and those all should be lowercase, but to make it let you see it better, F, you can have 14. On the test number 1, an important information, I'll give you this chart. A couple of years ago when I was teaching general chemistry, I made all the students memorize this. It's important, and I finally realized about a year and a half ago, am I testing your chemistry knowledge or your ability to memorize? I should be testing your chemistry knowledge. So good news, you don't have to memorize this, but you have to understand it. So we have the electrons. They're in shells and subshells. And that's one, how you can view that. Everybody got this down? If not, going once, twice, done. I'm turning the switch off for the next couple of slides. Another way of looking where electrons are called orbitals. You know, orbitals are a region of the atom where the electron, the highest probability of finding an electron. If I were the most powerful person in the world, in the universe, and I could stop all motion of everything, including electrons, boy, that'd be powerful. Stop, and everything, including electrons, to stop moving. The orbital inside of an area is where you find that electron. And you say go, and then stop, and you find it in that area. Again, switches off on this slide, but it's a good background information if you have other classes. And orbitals have shapes. Here are 2 of them. S orbital has circular. That means around in that circle, sphere, a certain distance from the nucleus. If I could stop electrons from, ooh, that would be powerful, but I'm not. But if I could, that's where you find it. P orbital has an hourglass shape. That means if I stopped it, the electron would be either here or here. And because of the shape of the p orbital, it affects certain things. How many of you have heard of that trans fats are bad for you? Anybody hear that? And that's because of a carbon-carbon double bond, be with you in a second, that switches off on this, that involves two p orbitals and makes it a certain shape, and that shape locks it in and affects your health. So when we ask, you might ask, why does anybody want to learn about it? Well, this affects the shape of molecules, and that shape affects how it works in your body to do good things or bad things. Question?
Could you just scroll up a slide?
What?
Could you scroll up a slide?
Go back to the left.
Yeah.
Okay.
Thank you.
You're welcome.
I'm good. Thank you.
Okay. This won't be on the test, but in case you want to know about it. Now, it turns out electron subshells are filled in order of increasing energy. And the electrons occupy the orbitals that I won't talk about, the subshell, that each orbital acquires one before a second one, that we won't go into, and the last one. So this slide, don't write down, unless you want it. And no more than two electrons can exist in an orbital. This helps chemists understand the chemistry, but for you, switches on. Now the question is, where are the electrons? Which orbitals, which shells and subshells are the electrons? And one way of showing that is called electron configuration. And I'll never ask what is electron configuration, but I'll ask you to know how to do this. So we have a statement of how many electrons an atom has in each of its subshells. And again, you use numbers and letters only. Seaboard, for example. Oh, I gotta get to work. I want to get this up. Now, let's look at the following question. 3 points each, so sometime in your future you might see this on a piece of paper. And the question is, give the electron configuration for I'll write it up here, hydrogen. How do you do that? Well, first thing you have to know is how many electrons does hydrogen have? And if you look over here, hydrogen, how do you determine that? The atomic number tells you how many electrons. Now, hydrogen, this you don't have to put down, but I will, has 1 electron. So how do you do that? When you're filling electrons in the shell and subshell, you start from the lowest energy, and then you fill till you get to the highest energy. So the first shell is 1. And we'll show that with the number. Now, we're actually showing where the electrons are going in the subshells, and the first subshell of 1, notice 1 only has 1. And again, you start with the lowest energy and go to the highest energy. And the first lowest subshell is S. And the actual determination or name is 1S. All subshells are made up of a letter and a number. So the only subshell in shell 1 is 1, S. And that's 1S. Now, how many electrons can we put maximum in 1S or 2S or 3S or 4S? 2. How many do I have to put in? 1. And we denote that by a superscript number. And that's how you do electron configuration. The lowest shell, you start out filling electrons 1. Is shell 1. How many subshells does shell 1 have? 1. And you start with the lowest energy, and that's 1s. How many electrons can you put in there? 2. Well, we only have to put in 1, so I'm done. Let's do helium. Same thing, electron configuration. How many electrons does helium have? You look over here, 2. So helium has 2 electrons. What's the first shell that you put electrons in? You always start the lowest energy, 1. So now I can look at that and say I have shell 1, what's the subshell? S, because you start at the lowest energy subshell, 1s. How many electrons can I put in S orbital subshell? 2. How many electrons do I have to put in there? 2. I'm done. And that's how you do it. Now it looks like I'm not going to go to the next one. We'll continue this on Friday. Everybody, heads up. If you have Thursday lab, don't forget to wear proper clothing. No cuts, rips in your jeans or leggings. Bring your safety goggles. Don't forget your to-do list. Don't forget the lab is that's due tomorrow. And please be on time with that. Drive carefully tonight with the snow.
Oh, yeah.